Welcome to the Intel Quartus Prime Software Design Series, Timing Analysis, Online Trading Part 5, Timing Exceptions. My name is Steve. In this course, I will go over SDC timing exceptions. Here are the recommended prerequisites for this course. An online training called Time Analyzer, Introduction to Timing Analysis, that can be found on the Intel FPGA YouTube channel or on the Intel FPGA Trading website. Knowledge of FPGA architecture and the design flow, and familiarity with the Intel Quartus Prime Pro software. If you haven't done so already, check out our previous courses listed here in this series of online trainings. Constraining your design tells the software tools your desired timing goals so that the fitter and timing analyzer can properly report back if your design can properly operate with the timing requirements. To constrain your design, you will need to understand the timing of the system environment, such as the board delays and time requirements of the other components connected to your FPGA. What if your SDC file is not exactly right, or some constraints are off by a little bit, or some constraints are missing? It probably does not sound like too big of a deal, but these incorrect or missing constraints can cause the fitter to make incorrect optimization choices and potentially spend too much time trying to reach timing closure in certain areas of your design where timing is more restrictive than necessary. And when the fitter works unnecessarily hard, then other areas of the design will suffer as a result. Not only will the fitter spend time on unneeded constraints, but the timing analyzer will spend time processing the incorrect constraints. This course is about writing SDC files for common Intel FPGA design situations. For questions about writing SDC, refer to these user guides and online helps. And there is the Tcl and command line help as well. I point out the Tcl and command line help because they are installed with the Intel Quartus Prime. When you're in the Intel Quartus Prime user interface, and you want a quick reference for a particular command, such as what are the arguments for a certain SDC constraint, if you're in the Tcl console in Quartus or in the console in the timing analyzer, you will notice a question mark at the left side of the slide. Click on the question mark, and that will open the command line and Tcl API help GUI as shown. It is basically the reference guide for anything scripting. Highlighted here are the SDC and extended SDC commands. The SDC section are all the standard SDC commands from the SDC specification, and the extended SDC are commands that Intel has added. I will now go over timing exceptions for SDC commands. Timing exceptions can be some of the more challenging SDC constraints that you can create. When you create your clock and I/O constraints, you are telling the software what the default timing should be for your design. Timing exceptions come into the picture when the default behavior does not encompass the complete idea of your design. Up to this point, with the timing constraints that I've gone over, you can fully constrain your design and have all of your paths covered by a constraint. Timing exceptions are necessary when you know that your design needs to deviate from the default behavior and an exception needs to be described. Timing exceptions that exist are the false paths, multi-cycle paths, and max and min delays. False paths mean that you do not want an analysis to be performed. False paths are sometimes referred to as cut paths. When you create a false path, the fitter, which is timing driven, is free to place and route the path as it sees fit now that there are no timing constraints on that path. A multi-cycle path constraint tells the software to adjust the default clock analysis on a specified number of launch to latch clock edges. The max and min delays applied to a path will override any clock constraint that exists and apply the value noted in the constraint. In this section, I'll go over false paths and multi-cycle paths. Here's the agenda for this section. I'll go over false paths, multi-cycle paths, and their usage. I'll talk a little bit about the priorities that the exceptions have, and finally, how to verify if the software recognizes the timing exceptions that you have in your design. Some examples of when you need to use timing exceptions are synchronizing an asynchronous signal into a clock domain, when you go from one clock domain to another clock domain, other instances where you will need synchronization hardware. If you need to over-constrain a path or set a path to have a higher priority constraint, such as using a max delay constraint. If you need more than one clock cycle to go from one synchronous element to another one. Logic that is used as a type of enable signal to capture data every 2 clock cycles or every 5th clock cycle and so forth. And static registers that rarely get updated and maybe don't need a fast clock constraint. The Intel Stratix 10 and Intel Agilex FPGA family's internal architecture style is known as the HyperFlex architecture. This architecture has registers everywhere in the FPGA and not just in the traditional location for registers, where it is a lookup table and register combination. The HyperFlex architecture has registers in the routing infrastructure and on the inputs and outputs of the block resources in the FPGAs, in addition to being coupled with lookup tables. The whole point of all these registers is that you can add a lot of registers for pipelining purposes to help increase your Fmax. To help utilize these extra registers called hyperregisters, the software has an extra stage in the fitting process called the hyper-retimer. For the HyperFlex devices, any timing exception applied to what is called an endpoint for the hyper-retimer, meaning the hyper-retimer cannot retime registers through these points. As a result, you should only use timing exceptions where you need them so that you can maximize the performance of your design if you are targeting the Intel Stratix 10 or Intel Agilex part. Fault paths can be divided into 2 types. Logic-based, which describes logic paths that are not relevant during normal circuit operation, such as test logic or semi-static registers. The other group of fault paths is timing-based, which means that the circuits are relevant during normal operation but have been encapsulated into a clock domain where the path should not be. The most notable example of this type of circuit is when your data path goes from one clock domain to another clock domain. Since Timing Analyzer treats all clocks as related by default, all paths will be analyzed against the clock domains in which they operate. The setFaultsPath command tells the compiler not to analyze paths that have been marked. This is true for both the fitter and timing analyzer. When you cut a path from analysis, the fitter is able to focus its efforts on other areas of the design, so the setFaultsPath command deprioritizes the path that this command has been applied to. I'll now go over some of the more common arguments for the setFaultsPath constraint. The from and to arguments identify the nodes or clock domains as the endpoints for the constraint. By default, both the rising and falling clock edges are used when cutting the path, but you can specify rising and falling edges from both the source and destinations with the rise from, rise to, fall to arguments. The through argument helps specify the exact path you want by identifying an intermediate path node through which that path will be cut. The latency insensitive argument was added to the setFaultsPath command to accommodate the HyperFlex architectures so that the fitter can retime into HyperFlex registers as needed as part of the optimization process. Here's the GUI option to help set up the setFaultsPath. When you click on the ellipses, the Node Finder GUI comes up to help you find the nodes that you're looking for. The SCC command gets updated as you fill in the fields. Here's an example of an asynchronous reset being synchronized to an internal clock domain. I could assert the reset asynchronously, but when I deassert the reset, the synchronizer will release it synchronously. The reset coming out of the synchronizer is synchronous, and the reset going into the synchronizer is asynchronous. Since the asynchronous reset does not belong to a clock domain, we need to put a false path on it as shown by the SCC command on this page. Here is some test logic that we want to cut out of the timing analysis. The logic is only there to capture value every so often and display it on the test output, so it is of little concern during normal circuit operation. To make sure we capture all of the logic in my test logic, I create false path constraints that will go from the clock to the registers in the logic, and then another false path going from registers to registers in the test logic, and finally, one last false path command to capture the paths from the registers in the test logic going to the output port. Here's a special case of the setFaultsPath command specifically for the HyperFlex devices. The setFalsePath command in this example uses the latency insensitive argument with the from and to values specifically targeting clock domains. With the constraint now added, the hyper-retimer will add pipeline stages on either side of the clock domain crossing. This path has to be truly latency insensitive, so you need to make sure that the data has settled. You will need to refer to your timing analyzer reports to determine how many pipeline stages were added when using this constraint. Both the setFalsePath and setClockGroups cut timing analysis between paths. The setFalsePath gives you more control on how to cut the paths in your design and is unidirectional, meaning you can cut a path from source to destination only if you want to. The setClockGroups command automatically cuts a path from analysis in both directions and is used for entire clock domains. Next, I'll talk about multi-cycle paths. You use the setMulticyclePath command because the default timing analysis on paths for the launch and latch edges do not describe the functionality of your design. This command adjusts the number of clock cycles between the launch and latch edges of the clock by adjusting which launch and latch edges need to be analyzed. Remember, whenever you use the setMulticyclePath constraint, that you are specifying how your design is behaving by telling the software tools to do an analysis that is outside of its default behavior. Setting up this constraint will make the negative slack go away, but be sure you describe the proper functionality of your design. Here are some examples on where to use the setMulticyclePath command. Certain paths in your design might not require a single clock cycle to transfer data from the source to the destination. If this is the case, and the multi-cycle path constraint is not applied, then the tools are needlessly working too hard on that path. You will want to use the multi-cycle path command if the source and destination registers have clocks that are integer multiples of each other, such that the source has a clock that is faster than the destination. Another example is when you have a clock-enabled circuitry that causes the destination to not sample the data every clock edge. Here is the setMulticyclePath command, along with the more common arguments that you use with the command. You use the start or end arguments, and they indicate whether the source or destination clock edge is being shifted. If one of these arguments is not used, then the analysis defaults to using the end argument. You will use the start argument if your source clock is at a higher frequency than the destination clock. The next argument is either the setup or hold, and that tells the tools if the setup is being adjusted or the hold is being adjusted. The default for the command is setup. The value field specifies how many edges are being adjusted, with a default value of 1 being used for the setup case and a default value of 0 for the hold case if no value is specified. Here are additional arguments to indicate the sources and destinations. By default, the rising edge of the clock is what is considered. You can clarify if you want rising or falling edges. There is the through argument as well if you need to indicate a path through a particular node in your design. Use all the arguments necessary to capture the paths that you are trying to constrain. Here's the GUI dialog box to help you enter the multi-cycle path constraint. I will now go over a couple of examples on using the multi-cycle constraint, which are extending the analysis window and shifting the analysis window. Here's an example of a standard single cycle transfer. Data will be launched from register 1 at the launch edge point in the clock waveform. The hold latch edge and setup latch edge on the second clock waveform represent the data capturing window. The hold latch edge means that new data has to arrive after that point, and the setup latch edge means that data has to arrive before that point. And this represents the capturing window. Data must arrive between the end multi-cycle hold of 0, displayed as EMH0, and end multi-cycle setup of 1, shown as EMS1. This is the default behavior for the multi-cycle path command, and is the default behavior for timing analysis. Now let's take a look at an example where the registers have a clock enable that activates the registers every other clock cycle. If I don't do anything differently with the constraints, the software will treat this circuit like it does with all the other circuits and analyze and optimize a path so that the data can arrive at the latching register in the data capture window of EMH0 and EMS1. If I do nothing, then this path is overconstrained, and the software is working harder than it needs to on this path to meet a single cycle transfer when it doesn't have to. In this case, we want to extend or open the data capture window. The first rising latch edge after the launch edge is not valid, so we want to tell the software that it's the second rising latch edge after the launch edge. I now have extended one part of the data capture window by implementing an end multi-cycle setup of 2 instead of keeping the default of end multi-cycle setup of 1. If I were to not modify the hold aspect of the data capture window, then by default, the data capture window would still be 1 clock cycle, and the hold portion of the window would just be 1 clock cycle behind the setup portion of the data capture window. This is the default behavior. Since I have 2 clock cycles to transfer the data, then I also need to modify the hold aspect, and I accomplish this by doing an end multi-cycle hold of 1, which finishes the multi-cycle constraint, and the data capture window has now been opened to 2 clock cycles. Expanding on the previous example and extending the window from 2 clock cycles to 3 clock cycles will give me a constraint where I need to end multi-cycle setup of 3 and end multi-cycle hold of 2. The data capture window has now been extended to 3 clock cycles. The second case is when you shift the window. This is still a single cycle capture, but the latch edge has a positive phase shift, so a multi-cycle constraint is needed. In the example, a PLL is used to introduce the positive phase shift. Register 1 is running on a non-phase shifted clock, and register 2, the latching register, is running on the phase shifted clock. Without a multi-cycle constraint, the software will do the default analysis and take the first positive latch edge after the positive launch edge as the capturing edge. With just the default timing and analysis, there is an impossible timing path from register 1 to register 2. Since the default behavior of the software tools does not represent the operation of the circuit, I place a multi-cycle constraint on the path from register 1 to register 2, targeting the clocks that I'm using in the design. I use the second rising edge from the launch edge as my latch edge, so that means I use a value of 2 along with my setup argument. When the setup edge moves because of the multi-cycle constraint, the hold edge moves along with it as a default. This is exactly what I want in this case. With a constraint added, this tells the software tools that the data has to arrive in a single clock cycle, but now phase shifted. And some will put the second multi-cycle path constraint in with the hold argument value of 0, just to be clear that this is the intended action. The 2 cases that I just went over, opening the window and shifting the window, are the 2 cases that cover most multi-cycle scenarios. You can find more examples of the set multi-cycle path constraint in the Intel Quartus Prime Pro Edition User Guide Timing Analyzer. This is another type of multi-cycle that you can do with the clock enable. You'll see that the clock enable is being generated by a clock divider type circuit, with the output being used as the clock enable for the other registers. Want to be able to apply a multi-cycle to all the registers. Getting all the registers that are controlled by the clock enable signal is not so straightforward using only standard SDC commands. You can create the names of the registers to make them more identifiable, or you could have a separate module where these registers exist, but if that was not done, then there is an Intel-specific SDC command called getFanouts that makes this constraint a little bit easier. The getFanouts command works when you specify the source of the signal, and then from there, the software will trace all the paths from that origin to find all the registers that that signal is fanning out to, and returns the list of those registers. The software will travel through combinational logic until the path ends at a register. All those found registers are then part of the collection. getFanouts only requires one argument, which is the starting point of the signal that is fanning out. Optional arguments allow you to be specific about a through point, not to follow combinational paths, or not to follow combinational paths with an inverter. This SDC example is the follow-on for the previous circuit diagram. The first line in the SDC sets a variable, enabled reg, which is the list of all the registers that are being driven by the signal coming from the Q pin. In the second line of the SDC, since the register enableReg is also being driven by the signal, it is removed from the collection. Now, the variable represents only the enabled controlled registers. Now that I have the variable set to contain the list of registers that are being driven by the enable registers, I can now create my multi-cycle path constraints based on my design needs. Next, I'll talk about the priorities of the various exception constraints. With exceptions in your project, they interact with each other in different ways. What happens if you have two different kinds of exceptions covering the same path, or when you have two of the same exceptions covering the same path, but there are different values? Always use report exceptions to verify that your exceptions are working. I will also go over how the tools prioritize overlapping exceptions. If you have the same path affected by different constraints, this is the priority list that the software tools use to override any overlap. The setFaultsPath and setClock groups have the highest priority so that once a path is cut, there isn't a way to uncut it. SetMax and min delays come next, overriding any clock constraint, allowing you to set an arbitrary time value on the clock edges for the from and to path. The setMulticycle path comes next, overriding the default setup and hold relationship, and the create clock constraints are last. Since the set input and output delay constraints describe the nature of the timing that is outside of the FPGA, there isn't an exception that will override these constraints. In this example, I create the clocks and constrain the input interface. The clocks are 10 nanoseconds, and I set up the input delay constraint such that the off-chip relationship has 6 nanoseconds to get to the register in the FPGA. Adding in a multi-cycle constraint targeting the DIN port modifies the setup relationship of the clocks that were previously defined, giving us 16 nanoseconds to complete the data transfer, since the input delay constraint was unaffected by the multi-cycle path constraint. Adding a max delay of 30 nanoseconds targeting the port DIN overrides the multi-cycle path and clock constraints that were there previously, now give me 26 nanoseconds for the data transfer, since the input delay constraint of 4 nanoseconds was still not affected by this new constraint addition. And finally, adding a false path on the DIN port cuts that path out of timing analysis altogether. This example just shows how the priority scheme works when timing exceptions constrain the same path in a design. If you have the same path and same constraint but different values, the last duplicate constraint that is read in will override all the previous duplicate constraints. In this example, I have a setup of 4 being declared on the path between register A and register B. Later on, I have a setup of 2 covering the same path using the same arguments, except now I have a setup of 2. The setup of 2 exception will override the setup of 4. The first multi-cycle path constraint that I have specifically targets nodes in my design and establishes a setup value of 4. I then have a constraint that more generally targets clock domains and creates a setup value of 2. The constraint that is more specific will take precedence over constraints that are more general, but only for those paths that overlap. There's even a precedence established for the same path and same exception, but a difference of arguments that are used. The highest precedence is targeting nodes, starting with the from argument going down to the to argument, targeting clock domains. The order of precedence that I went over is to make you aware of how exceptions can interact with each other and which ones take priority. It is very easy to have different exceptions in your SDC file targeting areas of your design and having other exceptions that end up overlapping the constrained areas. Be sure to run the report exceptions report so that you can verify how your exceptions are being applied to your design. That leads me into the last section on verifying the exceptions that you have entered. There are 2 reports that you want to use to make sure that your constraints get applied correctly. Report SDC, which will tell you that the constraints were read in correctly, including the timing exceptions, and the other report is report exceptions. Report exceptions is going to take all of your timing exceptions in all your STC files, whether you wrote them yourself or if they came from an IP that you created, and report on all the exceptions that were entered along with their status. Report exceptions is one of the standard reports you should run if you've entered in timing exceptions. With the report exceptions, make sure that the exceptions were targeting the correct paths and values and the exceptions were not improperly overridden. The report exception summary returns a status on all your entered STC exceptions. The reported status can be one of four, which are complete, meaning that the entered exception was fully applied and nothing overrode the exception; partially overridden, which indicates that some paths of the exception were applied, but other paths were not because of higher exception precedence. Fully overridden happens when the path completely overlapped with another constraint that had higher priority. And then invalid, which means that there were no matching paths in the entered exception. You may sometimes get an invalid status on exceptions from IP cores. Given the configurable nature of the core itself, there could very well be a feature of the core that was not enabled, but the core's STC file still had those exception constraints. A nice section of the report exceptions report is the multi-cycle path summary. This portion of the report will give some timing numbers based on the multi-cycle constraint that you entered, giving you a nice way to verify that your constraint is good. In the path summary, you'll find the setup end value extended by the multi-cycle constraint, and then how the data arrival and required paths were adjusted to accommodate the entered exception. It also shows you a wave diagram with and without the exceptions applied, giving you a nice visual of how your constraint behaves with a backdrop of a clock waveform. The top waveform has a line with the setup relationship as applied by the constraint, then a line if the constraint did not exist. The second waveform shows three forms of the hold relationship. On the top is the hold relationship as currently applied by the exception. The middle line shows what the hold relationship would be if only the setup exception were applied, and the bottom line shows if no exceptions were shown at all. In this course, I went over timing exception examples of false paths and multi-cycle paths and their priorities. I also covered how to verify your exceptions in reports generated by Timing Analyzer. This concludes part 5 of a 5-part series. I encourage you to check out parts 1 through 4 if you haven't done so already. There are many ways to get training about Intel FPGAs. You can watch hundreds of videos on our Intel FPGA YouTube channel, register for our e-learning classes on our Intel FPGA training website, or enroll in one of our regularly scheduled instructor-led online classes. Not only do we have quality classes, but they are also free of charge. If you still have questions about our FPGA products, visit our online forums. One more thing. We are always looking for ways to improve our training. Send us an email with your feedback about the course that you attended. My name is Steve, and thank you for listening to this course.